So in this class, I try to equip you with a combination of math and control engineering and MATLAB and Simulink. So every topic I'm covering, I try to transfer to the MATLAB and coding to make sure that you know how to work with MATLAB. Because in these days, if you don't have enough skill in MATLAB, Python, so you are not engineer anymore. Okay. So this is this, and and I told you in the morning class ME430 that this course is very similar to ME430. I'm sorry. So if you can drop either of them that you want, because I don't know why they are putting at the same semester, but this is what this is. So okay, so now let's go for the linear automatic control. Guys, please mute your speaker. Okay, I'm sorry, microphone, not speaker. Okay, as it seems, its name implies we are dealing with the linear systems. So for those of you that you were in my ME430 class, what do I mean by the linear systems? I mean that the linear differential equation, Can you see this, guys? Can you hear me? Yes? Or I'm saying LDN. So on the other hand, if you want to control a mechanical system, a thermal system, electromechanical system, fluid system, whatever, airplane, satellite, robot, first you have to derive this differential equation in undergraduate level. Sometimes it's partial differential equation in the very high level control in graduate and after graduate, postgraduate research. But here in undergraduate differential equation. Then because you want to work with the linear automatic control system or linear controllers, so you have to make it linearized. Okay, because this is the basic rule in the linear control. Okay, so if you have a nonlinear differential equation, your first mission is to linearize it to LDN. So how you linearize it? Using the equilibrium point. Okay, using the equilibrium point. I'm going to define all of those, but at the end of the day, after linearization, after you linearize, you have to be able to judge about the stability or instability of the system. You have to judge it after passing this course by looking at the poles of a given system that I'm going to teach. So you can judge about the stability and instability or range of stability of the system. After that, you can design a controller. You can design PID controller to make the system stable. So we are designing the PID controller to make system stable if it's unstable. To make it stable. To make stable. This is first mission, A. B. Modify transient response of the system. Transient response of the system. C. Remove error signal of the system. So this course mainly talks about these 3 items at the end. Clear? And so for part A, if I want to give you an example, so if this your system output is y versus time, suppose it's like this. Okay? It's like this. But you want the system, okay, follow a step function. This is the function, okay? Step function. But your system, this is input of the system x, y is output. So you see the system is unstable. So after designing the controller, okay, at the end of this course, you're gonna have this. This is mission A. Here we go. Mission A of the system. Clear? So modify transient response. Sometimes when you design controller or system by itself is like this. System by itself is like this. You see that if this is your car, when you're passing a bump, you have a huge overshoot. That's right. You are jumping inside your car. We name this overshoot or MP. I'm going to define it in this course, overshoot percentage. So this is, we name it transient response. This part is transient response. And we name here steady state because settles down. That's right. So sometimes you want to do this. As a control engineer, like as your car suspension system, you want to do this. You want to reduce the overshoot of the system. So this is your B, modifying transient response of the system. Clear? Sometimes I'm giving you a big picture of this course, okay? YT, output of the system. You want to follow the input step function, okay? Sometimes you design a controller, but at the end you get this. So here you have a steady state error signal because you have error signal E, error signal. So you want to design a controller, okay, that gives you this finally. Remove the error signal, see? So in any control system, undergraduate or graduate or a PhD course or postdoc course that you pass, for linear controllers or for nonlinear controllers, these missions is very important. Okay? See what I'm saying? Yes, guys? Huh? Good. So now let's go. Start with the examples. 2 examples at the same time. You have a pendulum and it's a particle pendulum. I explained previously in the vibration class. Here is amp, a lumped mass. This is massless link, L. But this pendulum base is moving with the distance x. Okay? What I want to do, you have to do as a control engineer. First, you have to derive its equation of motion of this system for controlling the system. Second, judge the stability of the system. Judge stability of the system. And finally, 3, control the system. See what I'm saying, guys? Control system. Okay? So, okay, I'm naming this point O. I'm gonna Why I select this example? Because I have a lesson for you at the end. If the angle theta is increasing, here is L cosine theta, here is L sine theta. So I have to plot the forces acting on the system. This is the force weight of that mg. Okay. So based on what I taught in the vibration or the dynamics or other professors did for you, I can write moment equation. Sum of the moment around point O is I-O theta double dot. Yes or no? Yes? Guys? Yes? Can I hear you? Okay. Obviously no. I taught this in the previous class, vibration class, a million times. You can apply moment equation around where, guys? Anyone remember it? Around fixed point or mass center. Mass center. This point O is moving X, so you cannot apply it. It's not a fixed point. See what I'm saying? Yes? So only you can, yeah, so you have to apply only here. Point A, say, mass center. Point mass center of this particle. Okay, so what we're gonna do, we're gonna use our lovely Newton. Okay, I'm gonna put a coordinate system x and y here. So I'm gonna say sum of the forces in x direction is mass of the pendulum, x double dot acceleration that, and the Fy is my double dot. Okay. So by saying that, we have to know all the forces. One of the forces is mg. Another forces is the reaction forces on the support area. So Fx and sorry guys, and Fy here. That's right. Okay, this is dynamics. So from here you get, okay, which forces in the x direction? Look at the picture and let me know. Only Fx. Minus or plus? Guys? Minus or plus? Here is positive, here gonna be negative. Right? Coordinate system. Right? See what I'm saying? Coordinate system, x, y. This is positive x, this is negative x. Clear, everyone? Yes? Okay. Minus Fx is equal to mx double dot. Now here, what are the forces in y direction? Negative mg, great. And yes, positive Fy, that's right, because it's upward, right? It is my double dot. So the point is that we don't have x double dot, acceleration x, acceleration y double dot of mass. So we have to calculate that. How? From dynamics. So r of mass with respect to point O, this mass with respect to point O is vector, position vector. Position vector of mass with respect to point O based on this is how much? L sine theta in I direction minus L cosine theta in J direction. Y minus because it's under the datum here. That's right. Yes? Yes, everybody? Huh? Clear, everybody? Okay. So are we done? No, here? No, this is parenthesis, bracket. Are we done? No, we are not done yet because point O also moving as x of t. Base is moving, so it is this. See what I'm saying? Yes, guys? Okay, because O is moving also. So the velocity of the mass with respect to point O is time derivative. L theta dot cosine theta plus x dot, the base motion velocity, in I plus L theta dot sine theta in J. Yes, O is the base, and we set it our coordinate system on the base motion. That's right, O. That's right. Yes, because in dynamics, if you pass ME220, the first step that you set up a coordinate system. The very first step in the mechanical engineering. So we set up our Cartesian coordinate system on the base of the system that is moving. That's right. See what I'm saying? So now we have to go for the velocity because we want to calculate x double dot y double dot. Can I go to next page? Yes. So, oh my God. So acceleration of mass with respect to point O is time derivative of velocity. L, let me do the bracket. L theta double dot cosine theta. See, first term in second term in first term. And this is parenthesis. Minus theta dot square. Oh my God. Sine theta. This is the derivative of the first term. This total. Plus x double dot bracket. Let me do it this. In I, unit vector I. Now this gonna be plus again L theta double dot first and second sine theta plus second and first theta dot square cosine theta in J direction. Is the algebra, guys? So now, having that, we found acceleration in x direction. This is ax, and this is ay, or y double dot. X double dot, y double dot. So I'm gonna put here minus fx equals this L theta double dot cosine theta minus theta dot square sine theta plus x double dot fy minus mg, second equation is, and you have an m here, guys, m l, just mx double dot my double dot ml theta double dot sine theta plus theta dot square cosine theta. I'm saying equation number 1, equation number 2. So we want to find, based on a control problem, first we are here still. We are here. Equation of the motion. But we don't know fx and fy. See what I'm saying? Now you can use moment equation, but around where? Based on what I said here. Around where? You tell me. Around? Yeah. No. O is fixed. O is moving. Do you have any fix? Yeah. Mass center. Mass. Point A. So you can say now. Let me change the color. Now you can say sum of moment around point A, mass center, is I around point A, theta double dot. Because we need three equations to eliminate fx and fy, and we derive the equation of motion. Guys, I told you this is a particle pendulum. What's the mass moment of inertia of particle pendulum around its own mass center? IA. How much is this? IA. Mass moment of inertia around its own mass center. What's a particle? Okay, guys, what is particle? Let's go back to ME220. What's the difference between particle and rigid body? Has no mass? Has no dimension? Yes, has no dimension. Everything has mass. Okay, everything, even atoms, even molecules. Okay, they have mass. Okay, so it has no dimension. So, and in the ME220, I hope that your professor taught you that I, mass moment of inertia, is r square dm. R is dimension. When the particle has no dimension, I is how much? I is how much? 0. So this side is 0 for the particle pendulum. For particle pendulum. So now it says sum of the moments around point O is 0. Okay, now let's go back to our glorious problem. Guys, does mg generate any moment around point A? Does? Why? Because it's passing through point A, that's right? Yes? So only fx and fy generate moment around point A. So let me do that. So you know that from statics and dynamic course, moment is force in the normal distance. So for example, here is 90 degree. Okay. So the moment of f is fx normal distance. Normal distance to the point A here is how much? L cosine theta. So you're going to have fx L cosine theta. Now positive or negative, because moments like force has sign. You tell me, positive or negative? Why? You are very right, but your judgment is very wrong. You were in my vibration classes, right? So that's why you know how to do that, but your result is wrong. Okay? Okay, guys. If I fix point A by my finger, okay, just fix it on the space. And if I apply fx, this link gonna go up or down? it's gonna come like down. That's right. Yes? No, I'm not talking about clockwise. I hate that. Okay? Don't tell me clockwise, counterclockwise in my class. Okay? That's for, I don't know what this is. Just answer this. If I apply fx around point A, so this comes down. That's right, this link. Yes or no? Yes? Comes down. When it comes down, okay, the theta increases. Yes? Yes, guys? So we want to increase theta. Exactly. This is our problem because it's moving upward. So it's helping to increase theta. So it's positive. Helping means positive. Here we go. Everybody understand? Okay. Good. Now Fy. Again, I'm fixing this on the space by my finger. Apply Fy. If you apply Fy, this link gonna be like this. That's right. So you're decreasing the angle. See, angle is being decreased. So you're resisting the motion. Gonna be resist means negative. Fy in the normal distance. Normal distance is this. L sine theta. L sine theta is 0. Equation number 3. Everybody understand now equation number 3, or you want to explain one more time? Don't be shy. This is your class. Clear, everybody? Yes? Guys? Good. Now, this shows that if I multiply the both sides of equation 1 by L cosine by minus L cosine theta, because minus and minus is plus, and I multiply the both sides of equation number 2 by minus L sine theta, and add the both equations, fx and fy goes to the hell. Let me do that, okay? Look at here, guys. I'm just writing. There is no magic. Minus and minus plus fx in L cosine theta, I'm writing on this equation 1, is ml, and we have also this here, guys, ml here is gonna be minus theta double dot cosine square of theta plus theta dot square, and L, one L comes here because it's multiplying by L. That is square sine theta cosine theta minus L x double dot cosine theta. Here we go. Now let's go for this equation number 2. Minus fy L sine theta plus mg L sine theta equals to m and minus, because here we go, L square, because we have one L, inside theta double dot sine square of theta plus theta dot square cosine theta sine theta. And now I'm adding these two equations together. Guys, all of you look at here, don't write. You have time to write. If I add these two equations, it's gonna be fx L cosine theta minus fy L sine theta. How much is that? How much is that? If I add these two, how much is that? 0. If I add. So from the left hand side, don't write, I'll give you time, okay? Don't worry. From the left hand side, remaining is mgl sine theta. mgl sine theta from the left hand side. Now you can write it down. Let me know when you are done. Okay. Minus here. Here you mean? Here? I mean here? Okay. It is theta double dot sine squared of theta. Because cosine is squared of theta. See? That's right. Because see here, sine in sine is sine squared. See? When you are done, let me know. I continue. Done? Okay. So now the right hand side. All of you look at here. Don't write. Minus ml square theta double dot cosine square of theta. Because we are adding. Minus ml square theta double dot sine square of theta. What's the result? I mean that it's going to be written like that. Look at here. Minus ml square theta double dot cosine square of theta plus sine square of theta. How much is this from high school? Yes, one. See what I have done? Simple like that. I will come here. Just bear with me. All of you look at here again. ml squared theta double dot sine cosine minus ml squared theta double dot sine cosine. They cancel out each other. That's right. After adding. Yes, anyone? Agree? ml squared theta double dot sine cosine. Okay. Minus ml squared theta double dot sine cosine. If you add them, they are canceling out each other. That's right. Okay, so we don't write it. Only remaining is this term. Gonna be minus ml square x double dot here cosine theta. Cosine theta. So now I can rewrite everything. So I'm moving this to the left hand side. So you're gonna have ml square theta double dot plus mgl sine theta minus ml squared x double dot acceleration of the base. This is acceleration of the base. That's right. Look at here, guys. Base moving with the x of t by itself. So it's double times acceleration of the base. So this m with this m with this m, this L with one of these L's with one of these L's goes to New York. So remaining is L theta double dot plus G gravity sine theta goes to minus L x double dot cosine theta. Or if you divide both sides by another L, you get theta double dot plus G over L sine theta equals to minus x double dot cosine of theta. And this is nonlinear differential equation of your leg when you walk. Yes, it is. Let me show you. If you assume that this is your hip joint that travels as x of t, and assume your leg as a pendulum, this is the equation of the motion of your leg when you move. Interesting, right? We simplified your leg when you're moving like this. So this is nonlinear equation of motion of the moving pendulum as a model of your leg when you move, when you walk, or when you run, if you simplify your leg as that. What's that? What do you mean? I cannot hear you. Can you repeat? I cannot hear you. Yeah, exactly. So this is your, say, your leg. I'm saying, let us assume it's like this. Huh? Suppose that my leg is broken. I'm putting in some cast. Okay, it's like this. Okay. Exactly. Okay. You got it. But why it's nonlinear? Because of this sine of theta. Why is nonlinear? Because of this cosine of theta. This nonlinear differential equation. Because sine of theta is a nonlinear term, or cosine of theta is a nonlinear term. So if I ask you go and find the solution of this nonlinear differential equation and I give you 10 years, you cannot do that by the knowledge that you have in undergraduate level. Okay? So what? No. What? Yeah. The equation of motion. This is how we write in abbreviation. Equation of motion. No problem. So we did first step for control. Now we have to talk about, judge about the stability of the system. Stability of the system, we have to first judge when we facing a system to control. We have to have a sense of the stability of the system, or if the system is unstable, how much is unstable. So we're gonna go there eventually, but for now I am assuming, okay, name of this equation is non-homogeneous equation, non-homogeneous differential equation. Why? Why non-homogeneous? Because the right hand side is not zero. We have excitation. Okay? Okay? But stability is an internal property of a given dynamical system. What does it mean? Means I want to see, without applying any force or any controller to control it, how system behaves by itself. By itself is stable, by itself is unstable, what it is. See what I'm saying? So that's why for now I'm making this homogeneous differential equation. What do I mean? I mean that I'm saying I forget about the base motion, okay? G over L sine theta is 0. I'm making the right hand side 0 to judge about the stability of the system by itself. By doing this, putting 0, I'm changing the problem because I'm saying that the base is not moving anymore. See what I'm saying? But I want to judge about the stability of the system. Okay. First of all, you cannot judge the stability of the moving pendulum. Okay. I intentionally moved the x double dot here because I want to teach you something. Let me don't do that because I want to do this minus x double dot cosine theta. Okay. Now, how to do that? First, I told you that this is nonlinear differential equation. You have to transfer it to linear differential equation. Okay. What are the nonlinearities in the system? Are sine of theta and the cosine of theta. So how we do that? We're going to do that by finding what, guys? Equilibrium points of the system. So we're going to linearize around the equilibrium point of the system. So at the equilibrium point, I hope that in the vibration they taught you, the velocity and the acceleration of the system is 0. Means that the system is at what? Is at rest. It doesn't move as it is. If you don't apply any external force or torque or whatever or excitation, system gonna remain there. Like as yourself, if I don't apply any force to your body when you are in my class, you're gonna remain there forever until you apply some torques to your joints to stand up and walk. So your body as a whole is in the equilibrium point of itself. See what I'm saying? Okay. Or for the translational motion, velocity, this is for rotational, and the acceleration is 0, equilibrium point. Or you are dealing with the pressure of a tank, rate of the pressure and the P double dot is 0. Or for the temperature of a room, rate of the temperature and T double dot is 0. Or, I don't know, for pizza dot, rate of pizza that you are eating, and the pizza double dot is 0. Whatever. Any dynamical system, I don't care. When I'm talking about the equilibrium point, mean the system, and it's a very trivial example is this. This is a ball, and if I put just a sphere here, exactly here, what's going to happen for that? If I don't apply any force, it's going to remain there forever, right? Yes? So this is the equilibrium point of the system. Exactly here. Say, if I say center is here, and here is theta is 0. So at theta, say pi over 2 minus pi over 2 is the equilibrium point of the system. I'm measuring from here. See what I'm saying? So exactly the same here. So equilibrium point of this system is, I told you, everything is 0. Everything that causes motion, okay? So here, because I said here is 0, this is 0. So the remaining is sine of theta is 0 for find the equilibrium point of the system. When I say equilibrium point notation, you have to put a star, theta star. This is convention. Okay. From high school, we know that this is sine k pi. Okay, sine k pi, and the k is 0, plus minus 1, plus minus 2, and forever. Okay, so I'm selecting k0. Oh, please don't, no. Oh, cancel. Oh my god. So I'm gonna assign a homework for yourself because you passed vibration with me or other professor. Why I'm not selecting K1 or K2? I want to assign homework for yourself, do it at home. I'm selecting K0. If I select K0, sine of equilibrium point theta gonna be sine of 0 because K is 0. So equilibrium point of the system is 0. Okay? Is 0. Means here. Get here, guys. This was our problem. And this is right. See? Theta 0. If there is no external force, we eliminate it. Okay? There is no external force. Pendulum gonna remain at theta 0. Here was theta. Remember? Here's theta 0. Here. This axis. And this is exactly based on reality. See what I'm saying? Okay. So now, based on the Taylor series expansion, because I have taught this in the vibration course and probably other professor to you, Taylor series expansion, Taylor series expansion, Taylor series expansion, which says y of linear is f of nonlinear at equilibrium point of that plus partial derivative of that nonlinear function 1 factorial round x, variable is x, generally speaking, at x is equal to equilibrium point and the x minus x star, and we don't care about the rest because the rest, as you know, is the second order, third order, is non-linear. This is Taylor series expansion. So having sine of theta is sine of itself at equilibrium point. Equilibrium point is 0. Sine of 0. Its derivative with respect to theta is cosine theta at theta 0 and theta minus equilibrium point. This is 0. This is 1. And you can say sine of theta is angle theta. So now I'm rewriting theta double dot plus g over L. Instead of sine of theta, we are putting what? Theta. So this is linearized. Equal to minus x double dot cosine theta. But still, you have this cosine theta because I'm linearizing whole equation. Based on the Taylor series expansion, cosine of theta can be approximated by cosine 0 minus sine of theta, because time derivative with respect to theta is sine of theta. At theta is 0, theta minus 0. This is 1, this is 0, because sine of 0 is 0. So you can write approximately as 1. around the equilibrium point of the 0, cosine of theta always is 1. So very linearized equation of the motion for the moving pendulum gonna be G over L theta, say minus X double dot. Bingo. Here we go. We linearize it. We linearize the internal dynamics of the system in the left hand side, and this is the excitation in the right hand side. Okay? Now we can judge the stability of the system. How? I'm gonna teach it on the next class. Okay? Guys? Any questions? Yep, so please stop me if you. And then after I finish the next class, we're gonna move to MATLAB. Okay? Okay guys, so let me stop it here. And let me save this.